This lesson is about classical decomposition models. It's part 1, focusing on additive decomposition of a time series using moving average smoothers. We will also talk about the R function decomposed. So in this lesson, you will be introduced to the notion of decomposing a time series into several components: the trend, the seasonal effect, the random term, using moving averages. You will see how we use that decomposition to put together a model for the time series that fits the data pretty well if the data follows the assumptions of the additive decomposition. The function in R that is going to do the job for us is decompose. Decompose requires a TS object. Your data must have been made TS class first. We will also see the calculations laid out for a simple example. Why is it important to know all that? Well, many time series associated with humans or nature exhibit trends and or regular seasonal effects. And it's convenient sometimes to be able to separate those components that always happen, they are regular, and use them for modeling or for removing them. That's what many data producing entities do. Many data producing entities remove the seasonality and or the trend before publication. That is, they do seasonal adjustment and or detrending respectively. It's important for people to understand what that means in order to avoid doing the wrong analysis. So as I said, many time series exhibit seasonality and or trends. Here is an example: lightweight vehicle sales. Obviously, lightweight vehicle sales exhibits a sawtooth pattern that reveals seasonality. Retail sales of beer, wine, and liquor stores also reveals a sawtooth pattern indicating seasonality. This atmospheric time series from NOAA also exhibits seasonality. Energy demand is also a seasonal time series. This data set, UK gas, which is a time series object that is part of the data sets package in R, in base R, actually, also has a sawtooth pattern that is increasing. If you notice, the beer, wine, and liquor stores retail sales also has a sawtooth pattern that increases over time. These are all examples of time series that have not been seasonally adjusted. So we can see the seasonal swings. You will only see the seasonality in a seasonal time series if the data producers did not seasonally adjust the time series. That is, if they did not remove the seasonal effect. How do we know that? Well, you need to look at the metadata. If you look at the metadata for the lightweight vehicle sales, you will see that it says the time series is not seasonally adjusted. It's monthly. That's how we know. You always have to find out before you start your analysis. So the additive decomposition of a time series with moving averages is going to extract the trend, the seasonal effect, and the random term, assuming that they are additive. Here is average monthly temperatures at Nottingham. This is the NOTAM dataset in R's package datasets. The decomposition that we do, additive decomposition with R, gives us this plot. The data set, the time series, appears in the plot at the top as the observed data set, as the observed time series. And decompose is going to decompose the time series into these components: trend, seasonal, and random term. The addition of the red terms equal the observed term. Here are some of the numbers of that decomposition. We're focused on the first 2 years. Because it's monthly data, we have 12 values for each year. The decomposition produces a term trend, and we are going to be using smoothers, moving average smoothers. That's what decompose uses. When we use smoothers, we lose some data. We lose the first observations because it's monthly. We are using a 12-month moving average, and that means we're going to lose 6 observations at the beginning and 6 observations at the end. And here we have some of these values that are produced. The seasonal the same is produced by the decompose function and the random term. Now, if you focus on one observation, July of 1920, the value of the data of the time series is 57.7. That's what we observe. Notice that that equals the sum of these red terms, 49 plus 12.967 minus 4.308. It's additive. We decompose it in an additive way. So the assumptions of the additive decomposition are that there is a time series trend, whether it's increasing, decreasing, or approximately constant, that can be traced. There is a rather constant seasonal increase or decrease relative to the trend. That's the seasonal swing. But this ST is going to represent not just the observed seasonal swing, but an estimate of it. The T sub T is also going to be estimated using the moving averages. We're going to use an estimate of it. And the assumption is that there is some periodicity, right? For example, S, the seasonal effect of a particular time T is the same as the seasonal effect at T plus S, in T plus S to S, in any multiple of S. So for example, the monthly Nottingham temperature has approximately constant trend and a seasonal effect that repeats every 12 months. If the data had been quarterly, we would have used S equal 4. And in addition, there is the random terms. So we additively decompose the Nottingham temperature data with moving averages using R's decompose. Here is the plot again for the Nottingham temperature. We use decompose of the TS object, which is NOTTEM. It's called NOTTEM. To see the numbers in the decomposition, we type decompose NOTTEM, the variable, that is the data set, the time series, a TS object, type equal add. To obtain the plot on the left, we type plot decompose NOTTEM. The default is additive decomposition. So if you omit this for additive decomposition, the type, it doesn't matter. You may extract components using the $sign. So let's make an object called components that contains all the, it's a list that contains all the components of the temperature data set. And then we extract the trend, we extract the seasonal, and we extract, and those are separate time series that we can work with. So in what follows, we are going to lay out a simple example to demonstrate the calculations that are behind the decompose function. Smoothing is a big area of research in time series analysis, and moving averages are a big part of that research. So get pen and pencil to double check your calculations. The source of this data is going to be a little book that was published in 2001 by Janasek, Practical Time Series. And it's just going to be acceleration values at different quarters. So consider this time series, which is quarterly. It has an upward trend, and seasonal swings are pretty regular in amplitude, as you can see. And it's quarterly, so the frequency is 4. This is different from the temperature data, which had frequency 12. The time series could be a good candidate for additive decomposition because it has sort of regular, seasonal, and a trend. What is a moving average to estimate the trend? Well, a moving average consists of just averaging values of the time series. And we usually do it taking into account the frequency. So if the frequency is quarterly, the little s will be 4. And this number here on the right with the star indicates where your trend is going to start. So remember that with the temperature, we did not start the trend at observation 1, but the trend estimate started in July. Well, here, if we have 4, the estimate is going to end up in the 2.5 observation, which is no observation because we don't have observations, 2.5, right? We'll see what that means in a second. This is what it means. If I average the first 4 terms, which is what a 4-term moving average, a 4-point moving average is going to do, the estimate is going to stay in the middle of 2 values. There is no observation at this point, so that's not very convenient. How we obtain that point? We obtain it by averaging the first 4 terms and by dividing their sum by 4. This computation. The second one was obtained by averaging minus 3.1769 plus 0.3484 plus 7.469 plus 4.4963 divided, right? And divided by 4. So successive moving averages are computed similarly until we include the last observation. So we use the term moving average because as we calculate these averages, we move along by dropping the most remote observations in the previous average and by including the next observations in the new average. So the name makes sense. Now, because 4 is an even number, we need to center the moving average. We don't want this situation of being in the middle. So we do another moving average of the moving average. We take a 2-point moving average. So we center, that's called centering, by taking a 2-point moving average of the new series. The column that has T hat, which is smooth, is the estimate of the trend. So notice how 2.1422 is an average of 2.00175 and 2.2842. So after we apply the 4-point moving average and then center with a 2-point moving average, we obtain the smooth series overimposed as an estimate of the trend. And we just represent it by these symbols, small little red symbols here. That's the center 4-point moving average, and it's an estimate of the trend. How do we estimate the seasonal component once we estimate the trend? Well, we can do it now because we have an estimate of the trend. There are several steps to do that because the seasonal effect is not the seasonal swing, it's by how much on average the time series value increases or decreases above or below what's expected from the trend after some adjustment. So it requires some calculation. The seasonal effect for Q1, for example, will be an estimate based on the average seasonal swing for all Q1 observations, plus some additional adjustments. So keep in mind that the observed seasonal swings are not the seasonal effects that we have in mind. The latter are going to be estimates. So let's start. The first intermediate step we need to take to find the seasonal effect is to calculate the observed seasonal swing each quarter. So the seasonal swing is going to be the difference between the time series and what we estimated to be the trend at that point, at that quarter. For example, for Q4 of 1960, the difference or the seasonal swing estimate is 0.3484 minus 2.1422. The second step, intermediate step to calculate the seasonal effect is to average the seasonal swings for each quarter. So you will take all the seasonal swings, all the numbers that appear in the difference column for Q1 and average them. So we did it for quarter 1, it gave out 3.799. Do the same for quarter 2. Take all the differences for quarter 2 and average them. Average for quarter 3 and average for quarter 4. So for quarter 4, for example, we took this difference minus 1.7938, minus 2.2969, minus 1.3256, 4.63. We added them, divided by 4, and that gave us this number, minus 0.195825. All right, so we're almost done. The intermediate third step is to make sure that these averages that we have calculated, these average differences, average seasonal swings, add up to 0. They do not add up to 0 the way we have them. In order to make them add up to 0, we need some little adjustment. So we first add all the averages and then divide them by the number of averages we have, which is 4. And that gives us the adjustment. Now this number is going to be subtracted from the average quarter seasonal swing that we calculated to calculate the seasonal effect for that quarter. So for quarter 2, the estimated seasonal effect then is going to be 0.2383, which is the average seasonal swing minus the adjustment. Same for other quarters, the average seasonal swing minus the adjustment, and so on. And those are our seasonal effects. Notice that now every quarter 2 is going to have this seasonal effect. Every quarter 3 is going to have this seasonal effects, an estimate of the seasonal swing. So now we have an estimate of the T, of the trend, an estimate of the seasonal effect, and we are ready to have a model. So if we estimated T, we estimated S, we can say that we can estimate the observed, or we can estimate the time series as T hat plus S hat. And of course, what's the W hat going to be? W hat will be the observed XT minus the X hat. So let's look at the T hat and S hat together. The S hat is, notice, has for each quarter the same values. Quarter 2 has 0.2383. Every quarter 2 is going to have 0.2383, right? So that's why they're called seasonal effects. They repeat every quarter. Quarter 1s have all the same seasonal effect. Quarter 2 has, we were actually describing quarter 2 before, right? So quarter 3 has seasonal effect minus 4.041. Well, all quarter 3s are going to have minus 4.041. Okay. So we add these two columns to obtain the estimate of the X hat. So the model fit. So the model fitted is the red line. And as we can see, it's not too bad. So everything that we have done for this simple example could be repeated by you by entering the time series into R, make it a TS object, and then use these R commands to obtain the plot, to obtain the trend, the seasonal, the random component. And that way you have now 4 time series: observed, trend, seasonal, and the random will be the difference between the observed and the estimated X hat. So the assumptions that we made is that the model is of this additive form, that we can estimate S, which in this model will be added to the trend, that the trend is locally linear, and the seasonal effect remains constant over time. That means we're expecting the pattern that we observed to repeat in the future. Unfortunately, we cannot forecast with this model, because in order to estimate the trend, we need to have data, right? We need to have numbers to calculate the moving average. And here is a little technical appendix for you, just to show you that this is called a filter in engineering. Engineers use time series a lot. And the filter is put together as follows. First, we did a 4-point moving average, and then we center by doing 1. This will be 1 divided by 2, 1/2, times 1, 1, times what we already calculated. So we end up really with a filter or 5-point moving average. That's exactly really what we ended up doing with the two steps, 1/8 times 1, 2, 2, 2, 1 multiplied by the time series for each successive moving terms, right? So what we notice in this lesson is that additively decomposing a time series into its components, trend, seasonal effect, and irregular component is tedious. However, the R software decompose can do the operation pretty fast for us. But seeing the calculations laid out in detail is useful to understand what decomposing means. And it's worth doing. The additive decomposition model that we can fit to a time series that satisfies the assumptions under which additive decomposition with moving averages can be done could be a good fit to the time series. But the assumptions that the same seasonal effects and trend shape will remain in the future must be satisfied. That is, the assumptions must be satisfied. I hope you enjoyed this lesson.